Okay, this is going to take us a little time to go through. I think I got it set up, but it probably took you a great deal of time to do this. I've been working on it a while myself. We're on 446. So we want to sketch an energy diagram, and my energy diagrams aren't that horribly accurate here, just to give you the idea. It's going to show you a conformational analysis of 2,2-dimethylpropane. And does the shape of that resemble ethane or butane? Well, let me do ethane first, because that's the one it resembles. So the energy diagram is going to kind of look like this: up, down, up, down. Let me show you what I mean. Let's do ethane, because it's simpler. And I'm going to steal one hydrogen off here. All right, so what you're doing is looking down the hydrogen this way, like a Newman diagram. Except for ethane, it's a circle with hydrogen, 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 and a triangle with hydrogen, hydrogen, hydrogen. Well, you'd be high energy, and then you're looking down this way. High energy, low energy as it's staggered, and then eclipsed, high energy, and then staggered would be low. Eclipsed would be high energy, staggered would be low, and all this would be symmetrical. The peaks would all be the same, the valleys would all be the same. Now, if it is this guy, 2,2-dimethylpropane, it looks like this. There's carbon 1, carbon 2, carbon 3, and a methyl and a methyl. So it looks like, how did I do this? I think I had to steal. Here it is. Here is 1, 2, 3 carbons for my propane, and there's a methyl, and there's a methyl off it too. So what it looks like, instead of hydrogen, 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 I've got methyl, methyl, methyl. So now what we're doing, what might be a little harder to see on this one, is we're looking down. This was the first carbon, this is the second. We're looking at how this hydrogen interacts with that methyl, this hydrogen, this methyl, this hydrogen, this methyl. If I'm staggered, I've got lower, lower, and lower energy, like here, here, and either one of those ends. If it's on top of the methyls, then it's higher, higher, and higher energy. So I've got eclipsed, staggered, eclipsed, staggered, eclipsed, staggered, and they're all the same. So the answer is it looks most like methane. Or if I do butane, if I pull this apart and do butane, there's 3, put a hydrogen there, replace this like so. Now I've got butane, 4 carbons long as soon as I put it together. What happened to it? What's wrong? I think I just wanted to go like so. There we go. Now, here's what we've got. Let's call this my front carbon. So that's not the one with the circle. So I've got a hydrogen, and a methyl group. Hydrogen, hydrogen, methyl. And on the back, I've got hydrogen, hydrogen, methyl. So on the circle, I've got hydrogen, hydrogen, methyl. Now, if we do that one, the lowest energy is this one. In the back, I've got a methyl off to, let's say, that way. So let me turn it like so. So in the back, I've got, get this out of the way. I've got methyl here, hydrogen this way, hydrogen down towards you. Up here, I've got hydrogen up, hydrogen this way, methyl here, and these methyls are opposite. So that would be here and here. This is the lowest energy off either end. If I rotate it this way, to where I've got a methyl interacting with a hydrogen, my energy goes up. If I rotate it a little farther, it goes down. If I rotate it this way, where I've got methyl interfering with methyl, that energy's high. If I rotate this way, another, let's see, what would that be, 60 degrees, I'd be lower, probably not this low. Then, I've got methyl interacting with hydrogen, so it goes up a little bit. And then the lowest is on either end, where they're opposite. So to answer the question, it looks most like ethane because there's not this disparity between the high peaks and lower peaks, and it's even all the way across. Now that's kind of a hard question, I guess. All right, let's go on to $4.47, and it's asking about kind of the same thing. We've got dimethylbutane though, so instead of butane, we've got a dimethyl. So I can pull this off of here, and now I've got a, is that 2,3-dimethylbutane, and let's put a okay, now I've got a butane, 1, 2, 3, 4. Got a methyl group this way. Got a methyl group this way. Right now I have them cis as opposed to trans. You know, and I think that would matter. Let me think about this for a sec. No, it would just be an inverted graph, I think. So if we look at the second to third carbon between this one, off of, let's see, this is the back one. Okay, so I'll put it the way you would see that. A hydrogen, hydrogen down, methyl and methyl up, down, up, and up. And on the front carbon, hydrogen up, methyl, methyl down. So if we rotate that around and draw the energy diagram, the way it is here, it's the least right here. I'm starting with, when you combine those two, this is what we got, and as you're looking down, this is what you should see, is I rotate it 60 degrees. Now I've got a methyl interacting with a methyl. I also have a hydrogen interacting with a methyl, so the energy goes up. If I go a little farther, it eclipses, the energy goes down. If I go a little farther, it's the highest, because now I've got methyl interacting with methyl, and methyl interacting with methyl. If I go a little farther, it eclipses, it goes down, or it staggers, it goes down. If I go a little farther, those two are eclipsed, and I've got methyl interacting with methyl. I've also got this methyl interacting with this hydrogen a little bit, and the same thing over here. And if I go a little farther, then we're back down to here where not too much is interfering with anything. Okay, so that's what the energy diagram should sort of look like. All right, the one thing I haven't done on these energy diagrams is punch in the numbers and try to make them accurate. It's close enough to get the idea, I think, is what's going to work there. Okay, let's go on to 448. And we've got to do the ring flip. Hopefully, imagine you had less trouble with this. If we flip this down, this methyl group becomes equatorial here. Hydroxyl group, move it up here, it flips out, the hydrogen is equatorial. And the chlorine, let's see, that's going to go up, and so it will be equatorial out here. B, if you flip the chlorine, if you flip the chair down this way, chlorine becomes equatorial. Hydroxide becomes axial, and this methyl group would be equatorial. You know, I don't have this set up to show you that. I've got it set up to show something else. If you have trouble with that question, you let me know and I'll show that to you on models. I need about 2 model sets to build both of these. And I think you're okay on this one. These looked real good before. And the last one, we're going to flip that hydroxide group down 2 positions over. This is going up, this is going down, so that'll be equatorial for that methyl group. Chlorine flips up and becomes axial. If you need help with that, let me show it to you. Okay, this part, once again, I had it right and then second guessed myself, and it is hard and it is confusing, and probably the better way to do it, rather than try to outsmart it all at once, is draw it out. Okay, so the cyclooctane. This one is going to have a higher heat of combustion than that. It's just basically it's got more bonds for one thing. That's the major factor. Okay, and then B, what you really need to do is draw the both chair conformations for this cis and both chair conformations for this trans, and crunch the numbers and do it. That's the probably longest but least confusing way to do it. I've worked through these and had them right, and then I start second guessing myself, and then I drew them out. It makes more sense. So on B, if you draw the cis, and on B, I've got this is my number 1 carbon and number 2, number 1 and number 2. These two are both up. That one's up, this one's down. So on a chair conformation, on the cis, I've got an up and an up. This one interferes at 7.6. This is what I've got set up. I've got trans set up on that right now. Okay. So here's cis. Here's my 6 carbon ring. That's going to be the same on all the rest of these. Hydrogen, this is up. Hydrogen, this is up. This is axial, this is equatorial. Right now, this one is interfering at 7.6. Now, wait a minute. I've got this one. This is interfering at 7.6 if I flip my chair the other way. This one's interfering at 7.6. If I make them trans, like B, this is a lot easier to do with models. It's going to take you more time, but it's a lot easier to do. If I make it trans, so this one's out of the page and this is down into the page. Let's see. Then I make a chair to where, let's see, this side's down. Here's my chair. There's the back, seat, foot. Okay, there's no interference with these up here. If I make my chair go this way, then this one's interfering at 7.6 and this one's interfering at 7.6, and that combination is about 15.2 because, let's see, okay, this one's interfering up here, this one's interfering down here. That combination is 7.6 plus 7.6 is 15.2, which means out of all these shapes, the one that's most going to be preferred is this one. So if it makes a trans, the shape will flip to go to that one. And then that energy is close to 0 relative to this. That means these are the higher energy with a higher heat of combustion. You might say, well, this one is. Well, the problem is if you make this one, it's going to flip into this shape right away. So you're stuck with this one. So cis is the higher energy, higher heat of combustion. Okay, so let's go to the next one. That's my story and I'm sticking to it. And then these all came out the way I originally predicted. So now we have same cyclohexane, but methyl groups in it. I'm going to call this the first position and this the third, first and third. I think that's how I did that one. So I'm going to move this down one. And what I'm starting with here is whatever it came out to be. Uh-oh, that's the wrong thing. Let's try this again. There, one's 3 position and one's the one's a 1 position, one's a 3 position. Now I'm actually starting with trans here. That's where I stuck it. So I'm starting with here's a chair conformation. Now I'm starting with this one upside down. Okay. Let me start with cis. And I can put it where I want a little bit better. Okay, with cis, if it's in this conformation, which is chair, here's the 1 carbon, here's the 3 carbon, here's the back of my chair, here's the foot of my chair, these are both up. So this is 15.2. If I make my chair go the other way, this way, down, and this one go up, all of a sudden now they're sticking off equatorial here and here, which is 0. So this is by far preferred. If I make this the cis version, it will just default, it'll flip into that shape and become preferred, which means the trans version, let me make the one, okay, when I did that I called this one 1 and it was down. That's what I had wrong earlier. And this is 3 and it was up. So you are looking at right now this version right here, where I've got the back of my chair, the foot of my chair, the seat, and then this one is down. As it's down, it's interfering here 7.6. This one is sticking off, doing nothing. If I flip my chair the other way, this one here comes up and interferes at 7.6, and this one goes off doing nothing. So this is a 7.6. So that means because this is going to default to 0, trans is the higher energy and the higher heat of combustion. And I'll do one more and then we're way over on this video. Let's move it one more position. Okay, so I'm doing this one where I've got cis both up off the first carbon. So if that's up, I can call this up. And then on trans, I'll flip that other one down. Okay? So on this one, I've got an axial and an equatorial. This is cis. If I flip my chair positions where this is down and this is up, I've got an axial and an equatorial. Both of those are 7.6. If I make one of those trans, it's this one, and flip this down and make this one trans by changing these two positions. Now, what's it doing? Now, if it's in that chair conformation, they're both sticking out there doing nothing, so that's 0. If I flip my chair, they're both up at 7.6, that's 15.2. If it's put in this trans position, it's going to go flip into the 0 conformation and stay there. And so these are the higher energy and the higher heat of combustion for cis. Okay, way over.